It's my pleasure to introduce Gil Kur, who did a PhD at MIT with Sasha Rakhlin, and who else?
Essentially with Aditya Guntuboyina.
Okay, I don't know that person, but I know Sasha very well, and is now a postdoc at ETH. I really like Gil's work. He's done a lot of very interesting work at the boundary of sort of convex analysis, statistical learning theory, high-dimensional geometry, and he's applying all these tools today to problems on benign overfitting, which I think is one of the hottest areas of deep learning theory, and I think Gil has some of the very best results. So thanks for being here, and take it away.
Thanks for the really warm introduction, Adam, and the invitation. It's a pleasure to be here. So the format will be the following: 10 minutes. I'm just going to give some overview, mention some nice facts to know, and then we're going to do whiteboard. So it's the first time I do a whiteboard talk in the US, so hopefully it will be okay. Also interrupt me, ask me questions when it is easier for me to understand if I'm clear or not. So the name of this talk, we're going to talk about Gaussian covariates on medium norm interpolation. I think in the last few minutes we understand why Gaussian is actually essential. Not essential, like essentially simplify the argument, and sub-Gaussian you have to work a lot. It's a based work of a very preliminary conference version at ICML, but we call it the medium norm interpolation meets the local theory of Banach space, and it's a joint work with my friend Pierre, which is in the Technion, Pedro that now is a postdoc of Roman Verschini and Irvine, and Fanny Yang from ETH. So we have a regression framework. So what is the thing? We have probability measure of some domain calligraphic X. We have some function class that all is in the same domain and output a real number. And we have NIID samples. We're going to assume the noise is Gaussian, which is actually quite important here for general results. And we have NIID points from this distribution P, and we observe those noisy measurements of F star plus Gaussian noise. And F star lies in this function class. And we have some loss function. And what we do is usually we do some empirical risk minimization procedure, which we take our data, which is the points, and minimize some loss. For example, if it's squared loss, so it's a least square procedure. So what we see in modern machine learning practice, we see that the loss, empirical loss, is very close to 0. For example, if we take LP loss, you really see that the observations are equal to the yi, to the noisy measurement. So we almost interpolate. And the idea, given the interpolation to those noisy measurements, say something smart on generalization error. The classical statistics philosophy says that if we have a zero training loss, we will have high generalization, right? Because we have noisy measurements, you would expect that this thing will not generalize well. So the solution was regularization. But what we see in the deep learning era, that if we take, that we see that those, we can get this zero training loss, but still generalize well. So the buzzword is interpolation is harmless. This was leading to line of 4 that is known as benign overfitting that says that given interpolation, tell me how can I generalize well. So the idea also that since these deep learnings are parametric and the number of parameters is actually quite big comparing to the number of samples. So the problem is that even linear models, when the dimension is much larger than the number of samples, we have many possible solutions. And clearly some of them will do well, some of them will do quite bad. So the model is to consider as a minimum norm interpolators. We have this MNI. What we say that essentially, you want to say that the ground truth is somehow some simple structure, and from all possible minimum norm, possible interpolants, you would like to choose one that has somehow a lowest norm. That somehow gives some bias towards the simplicity. So now I can define the setting again. We have a probability measure. We have some subspace of L to P. We equip our subspace with a norm. And our function class will be the unit ball of this norm. We have the same noisy observations, the NIID points on the domain, the corrupted samples of F star. Now it lies in this unit ball of this Banach space. And we have Gaussian noise. And the mu norm interpolator we can define as following. from all possible functions that interpolates the data, we choose the one with the lowest norm. So just it's important to know that if f star has a norm less than 1, usually we would expect that when we add noise, the norm of the minimum norm interpolator will be much larger than 1 because it's corrupted by noise. But despite this fact, we would hope it will generalize well. And our error will be in terms of the mean squared error. So mean squared error just means I take a new sample x, draw an IID from this distribution, see how close it is to f star, and then take the square, and then integrate over the data, because the data gives us randomness, and this fresh data point. So far it makes sense, this setting, or I'm talking to myself? Okay. So I'll give a motivating example, LP linear regression. We have IID Gaussian random variables, let's say. It can be also sub-Gaussian. We can just take the LP norm, which will be the LP ball here. So we just put in RD, and think that this D is much larger than N. We take the unit ball of the LP ball. And our NSC, since these are isotropic covariates, will be to measure how close is the mu norm interpolator. We're going to use this Wn hat here. It's close to this W star. So essentially, so it's important to know that the minimum norm interpolator is with respect to LP, but the generalization is with respect to L2. So this is something that is important to know. So let's say some prior work. So what is the reason we started this project? Because if you see most of theoretical results are when you have L2 space or RKHS, which is the L2 geometry. L2 geometry means inner product. Inner product means that this mu norm interpolator has a closed form. If you have a closed form solution, you can compute and estimate generalization. So the first work was of Peter Bartlett and his group. They gave some non-finite sample guarantees on the minimum L2 interpolator. And for this case, you can also put sub-Gaussian covariates. Because when you have closed formula, you play with random matrices and you get something.
Gil, even in that work, don't they need some sort of like bound on the effective rank?
Yes, I'm going to talk about this. So, but the bounds are also depend on the effective rank and so on. So, but you get guarantees. But if you want to get good generalization, the work is saying that you need to assume some sparse covariance, like low rank one or something like that. Then there was the work of Frederick Koller and his group. They essentially have like this local uniform convergence. Then they analyze the linear interpolators that are not in L2, when you don't have the closed formula. But there is a catch. I'll say maybe the catch here. So the catch is the result, it really needs, when you go from outside of L2 geometry, when all these results that study this case, I just mentioned two of them, of Constantine, our group, so they refined their bounds for the case of LP linear regression. I would say why this have this P here. These works are only more valid for Gaussian covariates, because in the end you boil something to Gaussian minimax and you compute. So when I saw that, I thought this is not the right thing. We have to maybe think in a different language. And also, this work was about to say that if we like L2 geometry so much, what we can say on benign overfit when we not working in the L2 geometry. So those works talk about this case, but only on Gaussian covariates in linear models. Then there is another work of my former PhD advisor Sasha and his former student Peng Yuan. They worked on the RKHS setting. There was work of Song-Man and Andrea Montanari. They worked on two-layer neural networks. And there was early work of both Misha, Sasha, and Sasha on essentially local interpolation schemes. So they reduced this thing to kind of low-degree polynomials. I will not talk much about this work. But the thing is, if you see all these works, it's actually somehow you boil down to things you understand about RKHS, L2 geometry, or use Gaussian covariates and CGMTs to say something smart. So what we're trying to do, we were essentially trying to relax the RKHS geometry, and we want to do it by connecting the generalization error of the minimum norm interpolator under the task of regression, and we need Gaussian noise, to the local geometric properties of the norm. So I was not too familiar with this field until a year and a half ago. But when you learn actually if you open the books on function analysis, you can connect those generalization errors quite nicely with ideas of uniform convexity, smoothness, type, cotype, and K-convexity. They are tightly related to this generalization. And what we're trying to do is to go from L2 geometry and linear models. So for this, we have to put two assumptions, and this is something that is important to know. Rather than being in Hilbert, there is a weaker condition that is known as two uniform convexity. So you want one side curvature. So a ball, the curvature is one, but you can only impose like one side, like they have a bit of lower bound on the curvature. And then you have some statistical assumption, because in the end, though we have the norm, which is a geometry object, we have also then IID points, and we have the distribution. So those things have to interact with each other somehow. So for that, we have to assume some assumption on the discrepancy between the empirical and population measures. And our main result is connecting to show that under uniform convexity, you can actually say smart things on the generalization error. And nice thing that it also gives, this approach, that we managed to show something on sub-Gaussian covariates without using the CGMT when P is not equal to 2. So when it was Hilbert, you can say something beyond Gaussian covariates, but when it was not Hilbert, all the work were only valid for Gaussian covariates. So these ideas from function analysis also help you to extend to sub-Gaussian covariates. So let's say two more slides and then we go to the whiteboard. So what is uniform convexity? This is something is really nice to know. The idea is the following. We have two functions, f and g, in our function class, in our subspace. Let's say both of them has norm 1, and their distance is delta. What is the only thing that it means that if you take the midpoint, the norm is a bit lower, right? So when you're in L2, you can do it by Pythagoras, and the optimal dependency is delta squared, right? So in drawing, it just means that if this is the unit ball, and those are two elements, if you take the midpoint, the norm is a bit less. So I would say this notion was defined in the 30s by Clarkson. I'll give you really nice few prefacts on those uniform convexity norms. So if you have uniform convexity norm, which is UC, call it UC2, you have concentration over Lipschitz functionals. So with respect to the uniform measure on the unit ball, and the metric will be a metric induced by this norm. Nice fact about UC2 ball, so if you want to do some chaining argument on the unit ball, so the curves and the Hadley integral are tight. So usually there is a gap by the square root of log n. If you're a bit familiar with empirical process, if you put uniform convexity, up to multiply the constant that depends on the uniform convexity, they align. So uniform, yes?
Very specific question. So the T is sort of a constant of convexity, but why is it delta square, not delta? Is that individual?
Oh, because it's delta squared. I think about, you have Pythagoras. Think about two functions on the, just like in L2. They're delta far from each other. Delta is small. You take the midpoint by Pythagoras, you lose delta squared over 2. Good question. I'll be that you ask questions. Good. But the nice thing about uniform convexity, it helps you to reverse inequalities. A nice thing about, this was due to Clarkson in the 30s. The LP norm when P is between 1 to 2 is uniformly convex with P minus 1 over 8. So when it's L1, clearly not uniformly convex, it's a polytope. But if you're a bit larger than L1, you have uniform convexity. Another thing that is also nice to know, that this definition is dualizing. So what do I mean? If we take the dual norm, we're going to first of all let me define what is uniformly smooth, and then I'll say why this thing is dualizing. So a norm is uniformly convex too, if I take two functions, one is norm 1, and the norm of G is delta. So if we take the difference, it means that you get 1 plus delta squared. So what is the idea? The idea is essentially to do some Taylor. So if you Taylor around this thing, you have FF. The first is the linear term, so the minus G will kill, and then you get the second order. So that's why you get a delta squared. So essentially uniform smoothness means that the Hessian is upper bounded from above of the kind of the unit ball. This is all due to Lindenström and Day. If your norm is uniformly convex, the dual norm is uniformly smooth with the same constant. here should not appear. Okay. The nice thing about Hilbert spaces, they are both uniformly convex and uniformly smooth. So essentially they have two sides. So when we work on uniformly convex norms, essentially we don't also assume this part. So Hilbert essentially are both convex and smooth with the optimal dependencies. So now time to turn off the Zoom and we go to the whiteboard.
Don't turn off the Zoom.
Oh, no, this thing.
You want me to raise the,
Yeah.
how do I do this again?
Okay.
The last button.
This one? This one.
Yeah.
So now we're going to do some whiteboard. So we will not essentially just want to mention how this uniform convexity and how it connects to benign overfit. So what we're going to do now, we're going to talk about essentially how to analyze mu norm interpolator in the case of linear model. So essentially the setting is the following. We have data points x1 to xn that are drawn. Let's start from simplicity from Gaussian. And D here is going to be a bit much larger than n. And we have observations. And the noise is isotropic. So the vector just means you take the n entries.
Gil, can you write just like a little larger?
Little larger?
Different marker or different marker?
Let's try different one. Okay.
That's flat.
So what we can
No, that's worse.
was so we'll stick to larger. So maybe a different marker is an option. Right. So what we do, we essentially define the minimum norm interpolator in this case. So P here is going to be between log D to 2. And so we are going to use the vector notation. We're going to choose from all possible W's that interpolates the noisy measurement, choose the one with the lowest LP norm. And we're going to work on a very simple question, actually super important to understand this behavior. If we just take W star equals to 0, we want to understand the generalization. So it's just going to be in this case, since it's a 0, it's just going to be understanding this error. So there are two regressor with 0. We're going to go, they're choosing the LP norm. I want to understand how this thing behaves. So when p equals to 2, it's easy to show the classical bound in this case that this thing will be of order n over d. So I guess you saw this thing probably in linear models, the n over d. The problem is that if you try to do the same thing from P, let's say you're going towards the worst case, the case that has the lowest uniform convexity, a naive bound.
This question is n over d or d over n?
No, it's n over d because
Oh, you switched. Okay.
no, because think about it, like we have more and more dimensions, so we're going to choose something with like much less energy. So d is actually in your side and n is against you. A naive bound will be essentially to get the following. Why is that? It's actually nice to, and actually also we have to put here square root of log log. And the proof is the following. What you can do is to use a very simple identity of if we want to understand the minimum norm interpolator with this observation. This is a really nice trick to know. What you can do, since our data is x plus some noisy measurements, it's equal to taking just the noise vector and taking the gauge norm that is defined by taking those covariates and taking the LP ball in RD. So this is a convex set, right? This is essentially taking a Gaussian projection of the LP ball. This is a convex set in Rn, so it's inducing a norm. And we just need essentially to understand this quantity. So the problem is, since you are in L1, in LP, and it contains the ball, the L2 ball in D, but has a very bad inclusion of half to the minus 1 over P L2D, it will cause you this inflation factor. So the variance here will look a priori huge. And if you know a bit of LP geometry, in the case of, let's see if this one works. Oh, much better. So for example, if P equals to 1, we know that those things that increase the diameter are the sparse vectors. So the motivation is to understand how to get N over D. So what we want to show that when P is or has a bit of uniform convexity, what we want to show that the expectation of this thing, of the minimum norm interpolator, will be essentially N over D up to some polylog. So we know that the diameter, though we have this bad inclusion, because as P goes to 1, the ball inside becomes smaller, we do want essentially what we want to show something like that. If you're a bit familiar with all these compressed sensing ideas and so on, is to show that even in this case, this vector is dense. So if your entries are dense, like, very essentially, so if you think about this drawing, if this is the LP ball, so we want to show that density means they are lying in a shell that is very close to the ball inside. So that's what we mean to be dense. If you have those dense vectors, which means that in this case, the norm in infinity norm is very close to the average L2 norm, up to square root of D, then you're going to get the N over this N over D that you want. So you want to show that things actually are dense, and I'm going to choose something with sparse. Because sparse vectors in LP geometry has a lot of L2 norm, which increase the diameter. But dense vectors are small. So this will be the idea. So how we do this, okay. How we do this, we develop like a nice method. It's actually quite natural, but a bit confusing. And this is I will put as a star, because it's like from the three things that I want people to remember from this talk. So star, we have kind of a landscape method. So when you have uniform convexity too, with some constant, you have something really nice that is happening. So let's stick to the notation of the projection. Let's think about this Gaussian projection as a kind of linear projection, okay? So if this is the LP ball in dimension D, with a bit of uniform convexity, and we take a projection of this LP ball, it will look something like this. It will look very close to a ball in most areas. You're going to have kind of spikes. And this phenomenon is actually because of the uniform convexity. Now we need another color. The spikes that you see here essentially corresponds to very sparse vectors. Let's say of theta. So those, if you're going really far, those spikes will be essentially the theta 1 sparse vectors. So what do I mean by sparse vectors? It means essentially vectors that are most of the mass in a small subset of coordinates. And all the points that you see here, most of the area that you're going to see here is going to come from an area that is very close to the John ellipsoid. So this area here will contribute, those parts are very close to a ball. And the spikes that you see here comes from essentially k that are n over log n spots. So it's actually quite nice what uniform convexity does. So essentially, all the range of vectors between k between n over log n, so I'll put here n. Essentially, everything, in some sense, goes very deep inside, and the only things that you see here comes from the d over log d dense vectors. So though this shape looks very far from L2 geometry, when you take random projection, because this is in Rd, this is Rn, and you're high dimensional enough, you're extremely close to be a ball, modulo some not too many number of spikes. And this is a property that comes from the uniform convexity, which is a really nice way to understand the landscape. So the motivation is that if you take the medium norm interpolator, you want to say it lies in these areas and will correspond to a dense vector. And all those things in between completely disappear. So let me show how to prove something like that. So I'm curious, how many people are familiar with Johnson-Lindenstrauss and Dvoretsky-Millman theorem? The second one, I'm curious more. Okay, so this is number one thing that nice to remember from this talk. If you have uniform convexity, essentially it kills a lot of directions, you get something very close to a ball and kind of spikes. Those spikes will be very sparse vectors. Second thing that is nice to know is Johnson-Lindenstrauss lemma. So what Johnson-Lindenstrauss lemma says, it says if I give you a vector in Rd, then if I will take a random projection, so this projection here is scaled by square root of d, this random projection, its L2 norm is of order n over d, where I put a square, so maybe, let's stick with v. So I will project v, and it will keep the length, up to the scaling of n over d. And this happens with probability of 1 minus x sum c to the n. Why is this thing interesting? It means that if you have e to the theta n vectors, and this is what we put it like this, and I'll put a high probability. If you have exponentially in n number of vectors, you can keep their distances. So if high probability, you can get uniformly for all those vectors that their distance is of order n to the d. So what essentially it means that random projection memorizes exponentially many directions from Rd. And the question is, since we are high dimensional, and we're going to talk a bit about the covering of this thing, we know that if you go more and more inside, the number of vectors you have to memorize their distance or something essentially becomes more than exponential in n. So the first thing to know in this case is the Dvoretsky-Millman theorem. So this is actually a really nice one to know. It means that if I know, I will define m star of a convex set K to be the integral of respect to the Gaussian measure with respect to the dual norm, and here I take a Gaussian. So this Gaussian is in Rd, we take a Gaussian, we see the average of its dual norm. So this is known also as Gaussian complexity, tightly connected to Rademacher complexity. And if we assume this K lies in a ball with radius d and contains a ball, then you can show something really nice. You can show that if you take the projection of this thing, it will be contained in this m star plus the diameter of this ratio. And here you can put a Euclidean ball. and is containing the same ratio. So what does it mean? It means that if the diameter and the Gaussian complexity are close to each other, then you can have a lot of directions in the set that are actually projected very close to a ball. So what essentially we know that if the number of directions you want to keep is greater than exponential omega n, but their diameter is not too big, this entire set projected to a ball, up to this discrepancy. Okay. So now what we can do is essentially, how much time do I have, by the way?
15 minutes.
Oh, it's actually enough. What is the reason? Oh. Yes, excuse me.
The place where you wrote naive bound, I'm a little bit I'm confused about the fact that n divided by d and the 1 over the square root log log, that they both come with a power 1. Based on restoring interpolation bounds, I would have expected that you would have p-dependent
What do you mean?
exponents.
I'm confused.
If you have a bound on the LP norm of a function p1, p2, then you obtain interpolation bounds based on the right-hand sides of this estimate. And these don't interpolate.
This one?
Yeah.
This is the if bound that is not true, we're going to push to this bound, even for small p. And we're going to show why. So the idea is essentially, if you think about this landscape, we want to show that in uniform convexity, essentially the sparse vectors, you don't have too many of those.
But when p goes to 2, then the right-hand side...
P goes to 2, this is n over d, but when p goes to 1, you're opaque.
But what about the log-log?
Oh, this is essentially, you can, let me fix this. So if we want to be more accurate, we have to put here p minus 1. This is the right scale.
Ah, okay.
Okay, sorry, it was as wrote this thing, I assumed that p. No, it's okay. I have it that someone follows, so that's good. So what will be the proof? So what we do, so the idea to, rather than using CGNT as black box, it is essentially to do the following. First of all, take this minimum norm interpolator and present it as a sum of delta k, vk. So what are those vk's? Vk's correspond to those theta k sparse vectors. And we have the following thing. Since we're in LP geometry, we can assume that the sum of these delta kp's is of order 1, and the scaling of the p norm of those vectors essentially will be 1 over m. M is essentially the object that says how much we have to inflate the LP ball to interpolate. So this is just a matter of scaling, and how you do this decomposition, you just take your LP vector and sort it based on magnitude on the entries. So the largest entries will be the one sparse vector, the two second largest will be the two sparse vectors, and so on. Since you're in LP, your sum is curved. And it will be of order 1, and you have to assume that all those have the same scaling. And
Gil, I'm kind of confused. What are you proving right now?
now I'm just going to show how to use those JL and
GL and the board.
and we're going to show essentially this is how the landscape looks like. Because this is,
Sorry, say it again.
I want to use this JL and Dvoretsky and entropy numbers on LP ball to show that literally the dense vector is the only thing that stays to some extent.
Okay, what does this have to do with the minimum norm interpolator?
Because the minimum norm interpolator, what you do, right? You have your observations, you start to inflate your LP ball until you find the first interpolant that it fits these points, right? Okay. So if you know, so this is the projected LP ball. And we start to inflate it, and then you know, since the noise is drawn uniformly from the sphere, you're going to hit it somewhere, right?
Yeah.
And you want to show that since it's like randomly on the sphere, so essentially you want to understand how a typical point here that you chose, where it maps to in the higher dimension. So you want to show that most of the things that you see in this projected world come from a dense vector.
Okay.
So to understand that this is actually the thing that is happening, you have to essentially kind of to peel the LP ball into sparse vectors.
Okay, let's assume that it does come from a dense vector.
Yes.
Why does that imply generalization?
Because if it comes from a dense vector, it will correspond essentially to the L2 case, because the L2 case essentially gives you those dense vectors, right? And which have low variance.
Yeah, and why do we have generalization in L2 again?
Because in L2, if you choose the non-interpolator, it will correspond to a dense vector. And you want to show that in the LP, it's the same thing.
Yeah.
So essentially, unless you have the
You're using it as a black box that for L2, we know the minimum.
yeah, you can compute it like it's a simple exercise.
Using like the close, using
Yeah, closed form or as an exercise, or from this amazing fact that ball is projected to a ball.
Okay.
If ball is projected to a ball, you get an over D. You want to show that essentially in high dimensions, when you're even LP, and this diameter is large, you still want to show you don't see those directions. So how you're going to do it? You're going to essentially use two theorems. The Johnson-Lindenstrauss lemma to handle the sparse vectors that have big length, and you're going to use this Dvoretsky-Milman to show that though you have some, when the sparsity becomes lower and lower, actually everything is projected to a ball. And actually it's really cool. When k is like decreasing and you have more and more density, the radius of the ball that you're going to see becomes larger, until you're going to see here these dense vectors. And this is the hack.
Thanks.
But it's actually, this is not even enough. I will talk about what you do. But it first of all starts to understand the landscape, because if you want to understand what is going on, you have somehow to understand how the landscape of the projected thing looks like, where most of the elements map, and then you understand what is going on in L2 in the upper thing. The really cool thing about uniform convexity, essentially it follows from the fact you have concentration, pseudocurve, the other thing is the same. The mass is very close, concentrated in small shell with relatively smaller diameter in this case. So if you have this decomposition, in order to say something small that you want to show that delta k is, you're going to use sparse, if you use a sparse vector and you give some weight to it, you want to show this thing is small when the sparsity is big. So when you have a lot of sparsity, you want to show that those deltas are small, and then it corresponds to dense vectors that have small energy. And the idea essentially is to show that we're going to use this thing and show something very nice. So when this is a result due to Schut, it's old school thing in 84, essentially you say the following. If you want to cover, those will be the k-sparse vectors in LP, and let me put here prime tilde because we want to scale it a bit. So LP tilde will be the LP ball a bit inflated. A bit inflated will be in John position, that the maximal ball it contains is of order 1. Then you can show that you can cover the set, so covering in terms of L2. So with just Euclidean ball, you can find essentially k over 2 to the k over log d over k balls with this radius, assuming that will cover this thing. So if we take this, so if this is the LP ball and those are the k-sparse vectors, so if you want to cover them, and this will be the radius. You have this radius. So what you're going to do is something really nice. You apply this Dvoretzky-Millman theorem on vectors that are n over log n, k over log n dense. This sparse will be at the wall. And what you have is little omega of n such vectors from this covering. You apply this JL over those ones. And then you're going to see, not JL, sorry, by Dvoretzky-Millman. So this is by Dvoretzky-Millman. You're going to show that those things are contained in a ball that is strictly less than log d L to n, when k is not dense up to a log, and when things are dense, you can show that those ones are contained in a ball with radius square root of log d, and also containing 1. Yes.
So this projection, is this again coming from the subspace generated by the base?
Yes, so think about is like I scaled everything that you think about spherical projection. So this is P. You can scale the noise to be of isotropic order over n. It will be like a spherical game that you see like essentially randomly from the sphere and kind of random projection. But what it's actually really cool that if you project those things between n over log n dense all the way to d over log d, most things disappear. And when you go to this d over log d, you literally contain this ball. So back to the drawing, answer the question. Back to this story, the thing that you're going to see in the boundary, most of the directions comes from those dense vectors. From the d over log d dense vectors, and all the other things between n over log n to d over log d, everything goes deep inside, so you don't see them. And this is actually a deep phenomenon to do to uniform convexity. Yes?
So to which extent is what you just explained dependent on I, the Gaussian?
This is actually a good question. So this I said like in 5 minutes I'm going to talk about this. Johnson-Lindenstraum's lemma, sub-Gaussian, right? This is restricted isometry property, Rademacher, so you're going to survive this one. This theorem is extremely vicious. It really depends on Gaussianity. Because in some sense to get this property, what you do, essentially you go to the dual body, and then projections are sections, and use the fact that average direction look like m star of the dual, which is m, with the mean norm, and then do a union bound. But to survive this expectation deeply depends on Gaussianity. Luckily, for the sub-Gaussian case, you are not going to show this log d. You are going essentially to take the fact you have a cube inside. And random projections of cubes, this is a result due to Cashin many years ago, because in the cube it's actually also easy to compute. Sub-Gaussian projections will contain a ball without this log. And this is cost you. This is not cheap. So for example, Gaussianity is really important for Dvoretzky-Millman. Sub-Gaussian, you can survive certain sets. So cube Cashin many years ago in Soviet Union. To show it for any finite volume ratios, this is a result due to Rudelsson, Roman, Bershin. They show essentially if your set has a finite volume ratio, you can still keep something like that for sub-Gaussian projection. In our case, this set does not satisfy this, the cube does. So if you go to d completely plus minus 1 over square root of d, you survive this. A bit beyond that, you don't survive this. So it costs you with square root log, which is a bit expensive in this case. But what is still remarkable that you can see, when you have uniform convexity, you have a lot of mass collapse. So keep things that are very close to the center of mass. All those things here in between, all the way to this n over log n sparse vectors, you don't see them. Everything goes deeply inside. And then you have those spikes. So how you handle those spikes, you're just going to apply, 5 minutes, right? Yeah. So, survive the spikes. What we are going to do, Can you delete it for Zurich theorem? So how to survive the things that are n over log n sparse? You know that the amount of directions that you have is t to the k over log d over k. So if it's n log n, this will be of order of 2 to the theta n. Then you can apply JL, because JL is memorizing those directions, because you know this thing holds with very high probability. You can take a union bond on exponentially many. So you apply JL on those ones, and you will notice that in this regime, the expected length, so if we take this thing, is essentially going to be of order n to the d, the true length, and this will be greater than square root of log n. Therefore, when you apply the JL, and you know to keep all these metrics, because you have less than exponential in n. If you have more around exponential in n, you can keep those lengths with high probability. And since their length is much larger than this radius of this ball here, this is of order square root of log n, you're going to see those spikes. So very sparse vectors are going to stay alive. So what we know that what you actually see in the projected world, so in the projected world, essentially what you see is the union of these d over log d dense vectors. So very dense ones, union of k between n over log n. So essentially, the projected image is essentially equal to theta k sparse vectors. So all the range between n over log n sparse all the way to very dense, between these two numbers, which is n over log n and d over log d, those things disappear in the projected world. You don't see those. You only keep dense vectors and very sparse vectors alive. So when I saw that, I realized that the mass, the mu norm interpolator, should be dense, and you get this n over d. But actually, it's much more delicate because it's not enough to show that those delta k's are sufficiently small to get this, but for this you do some variational argument. So variational argument means that if delta k is big, find another norm interpolator that has a smaller norm that is more dense. You do that, you're winning. But to understand how to even approach something like that, you start to peel LP ball to the sparse things. Mass come from dense vector spikes, not too many spikes outside. It should be okay. And it's actually LP gives you can compute things exactly, but for uniform convexity too, in the right position, this is actually a delicate point, you can essentially keep the same drawing. It's about uniform convexity. So all of using CGMT, black box, and compute, you start to understand the geometry of the problem, you start to say smarter things. So now we'll stop the talk and questions, comments.
Thank you.
We have time for a question.
Yes.
This is the naive question. If p is closer to 1, typically this is used to encourage sparsity in the solution.
Yes.
But you've shown that in fact, for p close to 1, nevertheless these projections give you something dense.
Yes, the thing is it's a hack. So there's a work of always to talk about this thing. I said that p is greater than 1 over log d. You have to keep convexity, uniform convexity alive. When you're going to the case of p equals to 1, you're going to be very sparse actually, because you don't have uniform convexity. In some sense, if you start to see, maybe here, the dependency in p is very bad, right? It's exponentially. So when p goes to 1, things become too big. You can't get the same thing. You have a bit to reduce tiny bit the exponent, and this log gives you enough uniform convexity to kill the sparse vectors. But it's not a continuous phase, so things somehow, you start to see more and more dense things when p is greater than 1 plus c over log d. But you become super dense when you're like log d. This is the right threshold.
So, I mean, is your result essentially saying that if we do want to encourage sparse solutions, we have to choose p less than 1 plus 1 over log 1d?
No, but this is about the variance. The problem with L1 mu interpolator is very bad generalizing because it gives you two like essentially noisy sparse vectors that increase the MSE a lot. So actually, when you're going to choose to be in this regime of the 1 over log d, you reduce the variance, but you keep a lot of bias towards the sparse direction because I try to convey it in this story. If your ground truth is sparse, you keep the length alive. So in some sense, a bit uniform convexity reduces the variance, but not increasing the bias too much. So this is the idea.
Any other questions?
Yeah, no.
Yeah, go ahead.
Yeah.
Can you give an example of spaces that are not Hilbert, but like have this UC2 property?
LP is not Hilbert.
Okay, is there another example?
You can do Sobolev spaces, random projections of uniform convexity. Things will not be Hilbert. It's a one-sided thing. So what essentially, you know that Hilbert spaces are very special. It's a ball, an ellipse. Ellipse is very nice. LP is not an ellipse, but you know that you have one-side curvature to some extent. So this is UC2. But I want to say it's not my ideas. A lot of smart people worked on those things. So.
Okay, thanks again.